We now come to our last speaker this morning, and I'm really looking forward to this presentation. Sarah Kurtz from the University of California Merced. She obtained a PhD in 1985 from Harvard University and is now a distinguished professor at the University of California Merced. After more than 30 years working at the National Renewable Energy Laboratory. There she did a range of things, but one of those leading efforts on PV performance and reliability, and which she'll be talking about this morning. And her work has been recognised with the jointly received Dan David Prize in 2007, the Cherry Award in 2012, and the C3E Lifetime Achievement Award in 2016, and induction into the National Academy of Engineering in 2020. So please welcome Sarah for her presentation.
It's a real pleasure to be here today. I thank the organizers, Ziv in particular, for giving me the opportunity. I've always wanted to come to Australia, and this is my first time, so it's special. We'll be changing the direction a little bit, re-engineering the energy system to reflect the opportunities by the new technologies is a really important and complicated topic. I'll move back to talking more about product development and how we introduce new technology. I am at the University of California now, but the work I'm presenting today comes out of what I was doing mostly at the National Renewable Energy Laboratory. And when I talk about products here, I am talking, I've had in mind here module development. I'm hoping that each of you will find something I'll say today to be relevant to some sort of product that you're developing. The University of California Merced, you may not have heard of before. It's a very new university. Here you can see all the cranes. These cranes are now gone, but it is a new university. We're considered at the gateway to Yosemite National Park. So if you ever come to California and go to Yosemite, I hope you'll stop by and visit me. I'll start today with the motivation. Obviously, we want to reduce the risk when we introduce a new product. Is it obvious? Really? When you get into the details, you find it's a little more complicated than what you thought. So we'll probably start by applying some stress tests. But what stress tests do we apply? I'll talk a little bit about how some of our stress test standards have been developed over the years. And I'll talk about some examples of how things were missed by those tests. And then I'll talk about how designing the product is actually just step one. You have a much bigger challenge when you move into the quality assurance part of your deployment. So your motivation is you want to sell a product, right? That's easy enough. It needs to work. And now you need to convince both yourself and your customers that it will work. Do you over-engineer it? Maybe that will introduce cost. What I've observed in the industry over the decades is that if you can make a product be rock solid and not add cost, then you'll do that. And then you have something that's more reliable. But if solving that problem and making the product more robust is going to add cost, that's where you get into a real dilemma. Do I make it be more expensive? Nobody wants to pay more for it. How much are we willing to pay for reliability and resilience? And this is a question that we all come against in many different aspects of our life. Do we pay for insurance? Do we go without the insurance? What do we do? A first step may be just to pass a qualifying test. In the example of the modules, we have IEC 61215 and some other safety tests and things. The customers, if it's a knowledgeable customer, the customers become accustomed to expecting that you'll be able to pass this. So chances are that will be a baseline expectation. Should you create your own test? If you need to create your own test that's going to be relevant to your specific product, is there something we can learn from others? This is where standards are designed to help the community. Can we share our knowledge together so that as a community together we can lift ourselves up? But having been in the role at NREL of trying to work with the standards organizations, I can tell you that what I began to really fully appreciate is that standards, we really want to have them a technical basis. In fact, at one point I took a stance of, well, I'm not going to work with this company because they're not looking for a technical basis. We want to have a technical basis for our standards. But then what I realized is that technically we shouldn't be writing any standards. Technically, we should be testing every product differently according to its own specific needs and its own specific applications. And technically, standards are just incorrect. So this is the paradox. We want it to be technically sound. I mean, nobody wants just an arbitrary standard that, like, we're just doing that test because, well, that's what people said. But what I discovered was that if you talk to the people who have many years of experience, they may give you the best guidance about which tests are actually useful, rather than you can do a complicated set of experiments to say this test identifies this problem and doesn't introduce this other. But it may be that when you apply that same experiment to a different product, you get a completely different answer. So you're always just looking at, like the one ear of the elephant or whatever. If you look with the people who have years of experience, they may have a wisdom that's better than a single test result. So it's a paradox that I really struggled with when I was working at NREL. And if you're looking at launching a product, I think you may have to struggle with it as well. So for standards, essentially my conclusion is that a technical basis is both essential and impossible. And so how do you deal with that? If we go back in time, JPL, the Jet Propulsion Laboratory, began a series of block buys in the 1970s. What they did was to go out, they defined some tests, and they said to the companies, if you can design a product that will pass these tests, we'll deploy it, and then we'll see what happens. And if there's a problem, we'll design a new test that will uncover that problem, and then we'll set a new set of tests. And they went through this cycle about 5 times or so. I can show you on this graph how the tests that they used for each block buy evolved. And what I'm going to show you on the next slide is how between block 4 and block 5, there's at least one report and multiple reports actually that showed that the success rate increased dramatically. And so I looked at that and said, oh, what did they do that was different? Which are the tests that really made a difference? And in the first red arrow, you can see there that they increased the number of thermal cycles. The number of thermal cycles tends to give you the failure rates on the solder bonds, and you get a mechanical fatigue that occurs when you temperature cycle the solder bonds. And by doing more of those cycles, they were more likely to uncover those kinds of problems. The second one originally was called a humidity test, but it evolved into a humidity freeze test. And it's actually, the freeze part turns out to be very important. What they ended up with was, first of all, they increased the number of cycles, but also they put it into something that's effectively like a steam bath. So it slurps up all that moisture. And then they freeze it really hard and solid, and the moisture expands as it freezes. And if there's any weakness in how your package is put together, it may break it apart. And then you see the problems that you're going to see with delamination eventually. So that's a test that turned out to be very valuable to many designs. And the third red arrow there you see was when they add the hotspot test, which is a way to identify how many bypass diodes you need in order to protect the module from partial shade or when a single connection between the cells gets broken. The effects of having the samples overheating because of going into reverse bias that's associated with these things, or arcing if you have a disconnection. These were leading to fires and fireworks in the field, which is not really something that solar wants to be known for. So this one study by Whipple in 1993 showed that before the block 5, they were seeing about a 45% module failure rate, and afterward they were seeing less than 1%. And of course, this I can't say that less than 1% holds on all products after that, but this is a pretty amazing improvement. Note that it started in the 1970s, and this analysis was in 1993. this sort of process takes 20 or 30 years to do. The good news is that it's been very successful, especially with our standard silicon modules. And you can see the data in this graph here shows that the majority of the failures in systems tend to be in the inverters. This particular study I've quoted here is in 2008, but I have yet to see another study since 2008 that really contradicts that. In general, we're seeing module failures. There are isolated incidences, which I'm going to talk some of them about when you have module failures, but in general, we're still, as a community, dominated by inverter and system level failures rather than the modules because of the good work of developing some of these stress tests in the beginning. So what are some of the things that might be missed? The standardized tests are designed to identify known failures. But if there's a new failure, you might miss it. And I want to give two examples here. One is that there's just a new failure mechanism that may have to do with a new part of your design. Another is that there might be a new stress. It might be a different location or a different system design. So I'm going to give next a couple of examples, and then I'll talk more about the strategies overall of how you can try to deal with the paradox. So potential induced degradation, I think probably many of you in this audience are well familiar with it, but I find it to be a really intriguing one because it's one where the system level design was so much more important than the module itself. So this is observed when there was a high system voltage. If you string a lot of solar panels together, each panel by itself doesn't put out that much voltage, but if you put enough of them in series, eventually you get a very high voltage. And if you put that together with inverters that didn't have the negative side of the string of modules grounded, you could begin to see a new failure mechanism. So this is an interesting thing, that there were modules that had not only passed all of the stress tests, but had been manufactured and deployed in the field for many years that now began to have a problem because there was a new inverter design. And the inverter didn't force you to have the system grounded in a certain way. And if it accidentally went negative, you would then see this. And so the cause was identified then, that a current would flow through the glass. Now, probably most of you think of glass as an insulator. Did you know it's actually a conductor? Under certain conditions, if you have a high enough voltage across it, you can actually have current flowing through the glass, and that will drive the flow of sodium, which can then go into the silicon solar cells and cause them to degrade. They found that there were three general approaches to solving the problem. One was to look at how you grounded the system, maybe not using the transformerless inverters, and then the sodium wouldn't move toward the cell. You could make the sodium move away from the cell. You could use an encapsulant that's resistive enough that it blocks the flow of the electricity. You could actually modify the silicon cell itself. And so people then scrambled, after they found that this was a problem, had to scramble to identify how you both design the system and or test the modules so to know whether there'll be a problem or not. So this is an unusual case where it was really the change of the inverter that led to a new problem more than the change of the module itself. But there are other cases where the module design itself may be a problem. And historically, the encapsulant in the module has been challenging. So the reasons why testing encapsulants are difficult, the acceleration of the encapsulant aging can give an inaccurate result. And taking time, this is the dilemma in the solar world. Everybody wants to launch a new product on maybe a 6-month development cycle. But you want something that's going to work 30 years. Can you test it in the amount of time? And so the question is, if we take the time to test this encapsulant material, will we miss the business opportunity of introducing the new material? So in the early years, the EVA formulation had been carefully tested by one company. They were not relying on the 6, 12, 15 test results. And so when new suppliers came online and just used maybe the 61215 test procedure, they found then that interesting things happened. I don't know if you can see this very clearly, but there are little kind of like lines that look like snails have been crawling across this, which is why these really have nothing to do with snails, but they look a little bit like people had crawled across it. And people then were quite concerned that their modules didn't look good. I maybe have an unusual approach to the world. I said to them, all of those little lines, those are decorating cracks that appeared in your cells. Why don't you market this as an asset to your module? This is like a crack detection system. But I didn't convince very many people of that. They figured out how to get rid of them, and that worked. But you do have to test longer for your encapsulants. And then once people figured it out, then they could solve it. So how do we avoid new problems? Obviously, you may add more stress. How much stress? What stresses? What we found was that over years, people were saying, I need to test this more. And all of the testing agencies said, well, sure, I'll come up with a test for you. And we had this long list of tests. And the question came up, could we replace these with a single test that would help people? Because what people were finding was, well, this module over here gave this result on this stress test, and then on this other stress test, it gave a slightly different, I have this other module that was tested on this other one. How do I compare those results? And it was very confusing and a lot of adding expense to the testing. And so this came back then to, could we create a single test standard? And this is when I got into really fully understanding the paradox of how do you get people to agree on a test standard when there is no correct test standard. They all wanted the correct test standard, but there is no correct test standard. So how do you do that? Now, an obvious thing to do is we could go back and do another series of block buys for some of the newer designs, but that's going to take 20, 30 years. And how much money? Quite a lot of money. So how do we approach this? Thinking about what you really need to do, if you're trying to age an egg, depending upon the conditions you use, you're going to get a very different result. So this is fundamentally our challenge. As a solar industry developing these modules, we want to accelerate 25 years into 3 months. Well, people would be happier to do it in 1 month if you could, but 3 months might be the maximum people are willing to really wait for things. Now, I would assert that if you know how to hatch a chick in 6 hours, you should probably go into the poultry business. But it is our challenge of how do we figure out how to accelerate all of these tests. So one of the things we looked at as we were looking to develop this accelerated test is, let's just consider a thermal process. How much acceleration do we need? And without going too much into the details of this publication, what you see, the conclusion was that the time in the test chamber might vary by as much as 10,000 hours, depending upon what the failure mechanism was. Okay, again, you're not going to get a single test result. If you're mounted in a different way, if you have a different, or at a different location, you have a different type of failure mechanism, how do you choose between that, those 10,000 hours? So it comes back to, it's essential to make something have a technical basis, but if the technical basis says it might vary by a factor of 10,000, then it's going to be impossible to design a single test. So what we came back with is the strategy of that for the IEC 63209, we want to design extended stress that differentiates rather than passes. We're looking at how do we not look at pass-fail, which gives you a black and white, but how do you compare this one to another one? How does it maybe compare to your previous product, or how does it compare to a competitor's product? And in part one, what we essentially did was to take the stresses in 61215 and make them be more severe. But we also added a second part, which is looking more at the material testing, which would take a longer time. Then finally, any of you who have done product development know that you really should do product-specific analysis. The FMEA, the failure modes and effects analysis, or other similar approaches is obvious. How is your product different from others? What are the failure mechanisms that you observe if you just take it out and see what happens to it? What are the weak points of the design? Can you duplicate the failures you observe with a really quick stress test? And then can you modify the product to perform adequately? Of course, the question then is, what is good enough? Just to challenge you to think about, do you really know what you're doing? You see this system was on a building in Washington, D.C. You can see these caution flags there that were kind of hung to keep people away from the PV system on that day. They look pretty harmless, but if you look at this infrared picture, you can see that wherever there was a little shadow there, it got hot. And so my question for you is, if partial shade can cause that much change in the temperature, what temperature are you going to assume for the temperature your module will operate under? This is something I get into a debate with for those who are developing perovskite modules. But just to keep in mind, it really is a good idea to address problems early on. The cost of addressing the problem is much less if you can design it at an early time. Then finally, the scale-up process. We did develop a standard to help guide the quality assurance you need during your increase in deployment. You aim to sell 1 million modules. Will the 1 million modules be the same as that original design you tested? The elements in this include alignment of the design lifetime with the product warranty, verification of the incoming material quality, traceability. If something goes wrong, can you figure out why it was and notify the customers who may have gotten the defective product? An ongoing testing program to confirm the consistency of your design and to get control of your manufacturing process if you find the manufacturing process drifted. Control of the solar simulator just to see if you got the nameplate power rating correctly. And then use of statistical methods for monitoring, improving the process, and continual improvement based on your field experience. So these are all kind of best practices that have been spelled out, and these are ways to get more confidence. In the end, however, if you're a small company, probably your solution is to buy insurance from a company that's bigger than you are. And that will give your customers the confidence they're looking for. However, note that the insurance company is going to want to see all this data I was just talking about. So my conclusions, the task of establishing confidence is both essential to your success, but it's really impossible to be 100% confident. So we have a lot of available tools. I hope that you found some of what I've said to be useful. Products are going to pass that standard qualification test. And then the standards that we have made are made because they're useful to the industry. That doesn't mean they're accurate, but do use them as a tool to get where you want. If you're doing a module testing, 63209 may give you some useful results, but you should still do product-specific testing. And keep in mind that when you go into production, quality control may be a bigger hurdle than the original product design. But finally, purchasing insurance might be the final answer. And thank you for your attention.
Thanks very much, Sarah. Do we have time? We have time for 2 questions. Well, sorry. Yep.
Thanks very much for the talk. Given some of your results you show where the climate you install PV modules in have a huge impact on their performance over a lifetime, what role do you see in the future for testing, product development, and in warranties to be climate specific for different PV modules?
So it's interesting that historically, like at one time, BP Solar had 2 different versions of their module they would sell, depending upon whether it would go into a region with snow, where they needed a more, they would use like a thicker glass or a bigger frame to be more robust. The ruling guide there is if you can make the module to be robust any place on Earth and get it to be the cost that we can buy modules today, then why bother to distinguish them? But if you can find that there's something that is adding cost to make it robust in that particular one, then you're going to need to differentiate. And when I did one analysis about what are the differentiators between different products, The aesthetics often is a key one. If you're going for rooftop, people would prefer to have it be kind of all black. And if you go into a utility scale, then having a white back sheet where you get kind of a checkerboard pattern is considered quite fine, whereas people didn't want that on their rooftop. So I found that aesthetics actually is perhaps the number one driver. But otherwise, you're mainly going for low cost. In my experience, usually people can figure out a way to design it to solve the engineering problem. Now, perovskites may be in a different category. I've been told that when they can fix every reliability issue, but each time they fix some degradation issue, it tends to add cost. So that wasn't a very satisfying answer. I apologize. I'd be happy to talk with you in more detail afterwards.
We have another question. Yeah, please.
Yeah, thanks, Sarah, for the nice talk. Thorsten Drucke from USW. You mentioned this approach of over several years, over decades, in fact, to adjust the testing methods to the actual failure mechanisms that are observed in the field. Now, that was probably fine in the back surface field solar cell transition to PERC took like 20, 25 years, but these development cycles are getting faster and faster. Transitioning to top column A is complete now, and then we may have other cell technologies in the future. Is there any chance that testing regimes will ever be able to keep up? They're almost irrelevant by the time these new technologies are coming online.
The standards typically do lag behind the technology development. And I think that's just a reality. I don't know how to get around it. There was one other question over here. No? I was quicker on that one.
So we are not cooling our modules. We don't put, say, panels on, so the convection would be, slower, etc. But many degradation problems have an Arrhenius behavior, but maybe some do not. What do you guess? How much would passive cooling of modules delay degradation and failures, or are the failures that are independent of failure?
So it's interesting to go back to those three that I showed you. And of those, like the first one was the thermal cycling. And so if the cooling would limit the extent of the thermal cycling and the rate of the thermal cycling, then that would be helpful there. The second one we were looking at was more the delamination, where you get the humidity freeze sort of approach. That has often been observed to be dependent largely on UV weakening of some of the bonds between, say, the encapsulant and the glass. It is true. So encapsulant discoloration has been shown to be largely a thermally driven process. And so in that case, cooling it. But if you can also, if you can reformulate the EVA itself doesn't tend to have a problem with discoloration. It's all of the things you put into it to make it have different properties. So I guess the short answer to it is there are some failure mechanisms for which the cooling slows things, but there's some other failure mechanisms for which it doesn't really have much effect.
Thank you very much. Thanks, Sarah.